Hey, what's up everyone? So last time we looked at alkenes and we looked at isomers for C6H12 and we said that there's 13 alkenes, my goodness. Then I said at the end that there's more. And you're probably scratching your head thinking, what? What other combination can there be? Then I also said think outside the box. And here it is, let's think outside the box. 13 alkenes, that is it. But that doesn't mean that C6H12 is it too. Because I can tell you right now that this is also C6H12. If you don't believe me, count all the carbons and count all the hydrogen. It is C6H12. But don't tell me that it is an alkene. This is not an alkene. If anything, this is a cycloalkane. This is cyclohexane. But it's still C6H12. So that's a snake question if you think about it. If this is cyclohexane, obviously I can have more other cyclic structure that will still inherit my C6H12. Like this one. Like the cyclopentane. Actually, there's only one of them. This also has 6 carbon and 12 hydrogen. This is called methyl cyclopentane. Now, some people might be saying, how come you don't write a 1 here? Do I have to write a 1 here? You can if you want, but if you think about it, there's really no need to. Because other than 1, where else would you put that methyl? Right? But if not, it's not wrong if you write 1. Just writing too much where you don't have to. And then there's this cyclobutane. And I would need 2 methyl group or 2 other C's to make a C6H12. So here it is. Now this one you might need numbers because there's other places where I can put this. So that's 1,1-dimethyl cyclobutane. Okay, so what other cyclobutane are there out there? Well, I can start moving around those methyl group. Oh, look at this. I can do this one. This will be 1,2-dimethyl cyclobutane. Right? Hey, can I move more around? Sure, why not? You can do this. That's totally legitimate. That's 1,3-dimethyl cyclobutane. Can I put this here and do 1,4? Now, if you do that, it's the same thing as this, so don't be silly. What else can I do? Can I do more cyclobutane? Yeah, I can do one more. I guess you can find one more cyclobutane, and it looks like this. Won't be a dimethyl. It will be an ethyl. So you have an ethyl cyclobutane. Whoa, look at that. So many. And I'm not done. No, I'm not. I have more. Because I can go on and look at cyclopropane. I just need 3 carbon groups coming out, right? So I have this one. This one is cool. Look how cool this looks. Looks like a weapon. Okay? So this will be 1, 2, 3 trimethyl cyclopropane. And I'm going to have a whole bunch of these cyclopropane. I just have to move these CH3 around. Okay? I can do this. Why not? Move it like this. This will be 1, 1, 2. Right? I will count this way. 1, 1, 2. trimethylcyclopropane. Cool, huh? There's not too many trimethyl. I guess really not that many. Okay, and then we can go ahead and do some other fancy stuff, like make one ethyl, like this one. This is still C6H12, but obviously I'll have a different name. It'll be 1-ethyl. This one is tricky, because sometimes you have to think, oh, who should I assign carbon number 1 to? Well, in this case, you assign it to the one that is lower in alphabetical order. So this is 1-ethyl, 2-methyl, cyclopropane. Right? If I can do something silly like this, make them all go in one, like that. So that will be propyl cyclopropane. So there's really a lot of different neat ways where you can actually put together the cyclic structure. I mean, the question is, really, are there any more? Man, my head hurts. Really hurts. Are there any more? Maybe. Who knows? But the point here is, you're going to have to think outside the box. When people say, give me all the isomer of C6H12, don't just think alkene. They really mean all the isomer, unless they ask you, hey, what are all the alkene isomers for C6H12? Right? Because if they say C6H12, any of these guys can be part of that group. And that becomes, dangerous if you don't think about it. All right. There's actually one more. And that's this. CH2, CH3, CH3. Right here. That's another one. So let's finish off with this one. I don't think there's any more. If there is, please tell me on the chat. Oh, man, I almost named this wrong. So that's 1-ethyl, 1-methyl, cyclopropane. I really think that's it. Okay. So how many are there actually? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my God, 11. So we have 13 plus 11 cycloalkane. So that's 24. Wow. So there's like 24 different C6H12. So when somebody asks you, give me some C6H12, and it's probably a good idea to tell them, which one are you talking about, man? Because I can figure out at least 24 different variations. That's not including what I'm going to tell you today. There's actually more than 24. Your head is probably blowing up right now and thinking, are you serious? Just body me. Just body me. Well, before you get bodied or want to get bodied, you still have to learn this. This is called geometrical isomerism. Okay? All the isomers that you've looked at so far are called structural isomers. It's because they differ structurally. No kidding. But then there are some of these isomers that are not differ in terms of structurally, but geometrically? What do you mean by that? Well, what I mean by that is location of substituents. Let me show you what I mean. Okay? This geometrical isomers I will get to later on again when we look at isomerism. But let's just say it's probably good to know it now. So the example here is butene. Some people say 2-butene, no big deal, same thing. Okay, but let's say butene. So the alkene is between the second and the third carbon. We know that because this is exactly what you would have drawn me if I asked you to draw 2-butene. But. Here's the problem. There are different variations when you draw 2-butene, especially when you put the double bond into a scope. Now, if you were to build this or look at the Vesper structure of this carbon or this carbon, you'll notice that it is single bonded to a carbon, single bonded to a hydrogen, and double bonded to another carbon. That is 3 bonding partners with no lone pairs on carbon. 3 and none. 3 and none. In Vesper, 3 and none gives you a trigonoplanar structure. Let's take a look at that. Let me draw 2-butene a little differently. I'm going to emphasize the geometry just on the double bond carbon. Okay, so as you can see for this carbon, I have that geometry where it is trigonoplanar, that the bond angle between each is exactly 120 degrees. Okay, so I'm emphasizing this right here. Now let's take a look at what this carbon is bonded to, which is this carbon. This carbon is bonded to an H. Okay. And this carbon, the same carbon, is bonded to a CH3. All right, that's cool. Same with the other one. An H and a CH3. Let's number these guys. This is carbon 1, 2, 3, 4. So basically what you have here is carbon 1, 2, 3, 4 as well. Okay? Now, I'm going to draw this again. C double bond C. Here I have an H. Here I have a CH3. But what I'm going to do here is that on the other side, right side, I'm going to flip the 2. I'm going to have H down here and CH3 up here, whereas in the other one I have CH3 down here and H up here. I'm going to number it too. 1, 2, 3, 4. Because the numbering is very important. Now, you may be thinking to yourself, what is the difference? They look the same to me. Well, kind of. They don't look exactly the same, but they seem to be the same. This is 2-butene. This is 2-butene. They're both 2-butene. Does it mean that these things are flipped? It automatically makes it different? Yeah, it does. This is what we call geometrical isomers. In biology, this one is a big deal because let's say if this is an enzymatic reaction where it involves enzymes. If your enzyme looked like this, notice that this guy fits perfectly to this configuration. But if you have the same enzymes, ooh, ugly. Now I don't know how to draw this back. This really doesn't fit as much because this is too small to fit into that active site. So as a result, these guys are not really the same because you don't look at them being the same. Under a wide scope, they actually look different. In fact, they have different chemical properties because they have different physical properties. That's how crazy these geometrical isomers can be. Right? So because of that, they actually have different names. Wow. That's why C6H12, 24, right? There's more than that actually, because for every alkene, some of them at least, you can have geometrical isomers. And with geometrical isomers, you will inherit different name. So let's name them. Okay? To name them, you need to know the direction of those long chain. The longest carbon-carbon chain is the key in terms of naming them. And in this case, if you were to circle the long chain, it looks like the two ends are both sticking at the same direction. Now, mind you, I can flip both of these and I can have going upwards as well. As long as they're really pointing at the same direction, we call that cis. Okay? Now, if you look at the one on the right, if you were to circle the longest chain, it seems like one end is pointing down and the other one is pointing up. That is known as trans. Okay? So in reality, this is called cis-butene, and this is trans-butene. Now, you might have heard of like cis fatty acids and trans fatty acids, which is really bad for you. That's where they got the idea from. Okay? Being in a trans configuration will actually make this structure of 2-butene more bulky. It has a little what we call kink to it. Whereas in a cis configuration, it's less bulky. As I said, very different. Now, there's a little thing that I want you to know, and that's bond rotation. Okay, single bond can be easily rotated. Okay, you can rotate these things as much as you want. Nobody cares. But hey, you cannot rotate double bond. This is pretty static. This is composed of a sigma and pi bond. You cannot rotate these things. Hence, when they're made like this, they're made like this. You cannot rotate and try to play around with them to make cis looks like trans. Now, that's not possible. If it's cis, it stays cis. If it's trans, it stays trans. Okay? So, make sure this is something that you know. And this is pretty much what geometrical isomers is all about. Okay? So, just to give you another, just a summary, that if you number the carbon according to how you number it when you draw it, if the numbering gives you the overall direction where they're sticking at the same, I guess, geometrically, that's a cis configuration. If your longest chain is built where one part sticks one direction and the other part sticks the other direction, that's a trans. So, hey, hopefully you guys are happy with that. And let's take a look at another example to see if you're able to kind of figure this out. Okay? So let me write that down here. Oh, let me just clear the screen. Okay. Yeah, let's take a look at another example. Nope, let me use, oh my goodness. All right, example 2. Okay, let's do this one. I guess if you were to name this is actually called 3-methyl hextuene. Right? This is 3-methyl hextuene or 3-methyl 2-hexene. Doesn't matter. Whatever way you like it. Let's say I want you to draw two configurations. I want you to draw the cis configuration and I want you to draw the trans configuration. Now, how would you do that? Now, the answer is very simple. Make sure you number these guys according to the longest chain. And you want to make sure, okay, if you're looking at cis, that this part is sticking in one direction and this part is sticking at the same direction. So let's go. Let's emphasize the double bond, okay, in this geometry. 120 degrees. So let's say you might want to, so this is going to be carbon number 2 and carbon number 3. Where would you want carbon number 1? So let's say I want carbon number 1 up here. This is where I want carbon number 1. That's this right here. That means I'm going to put H down here. See that? So this is 1, 2, 3. Where I'm going to put carbon number 4. Because carbon number 4 will link with 5, which will link with 6. Well, since carbon number 1 is up, I better make sure that carbon number 4 is also up. So I would not put it down here. No, 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 no. I would do this. CH4, 3, CH4, what did I say CH4? And why would I write 3? Okay, so because this is going to be carbon 4, 5, and 6. I will put that lonely methyl group down here. Okay, there's the showing of both of your long chain being pointing at the same side. Oh, lots of words here. So the answer of this, of course, is your cis 3-methyl hextuene. Okay. Now, once you draw the cis configuration, the trans configuration will be just as easy to draw. So here's your, just so you keep one side the same and just flip the other side. Gosh, just flip the other side. There you go. Okay, let's number these carbons so you know where they're coming from. Okay, and like this. See, pointing at different direction. So that's cis and trans. Okay, now there's more to this. There's actually a little bit more to this because cis and trans can also be abbreviated in terms of cyclic structure. But we'll save that for another time. We'll save that more towards the end. Okay, so let's take a look at another type of geometrical isomerism where we don't use cis or trans, but we use something called E and Z. I call it the easy way. Yeah, it's pretty corny if you think about it. So let's take a look at what is this easy way. This is called EZ isomerism. Okay, and here's my example. Let's do this CH3. Let's have a Cl here, F here, and I here. Let's do this. It's pretty cool. I like this. I like this. If you were to name this, this will be 1 ido. Oh my goodness. I lost my alphabet. Okay. 2 chloro. Okay. 1 fluoro. 1 iodo. Pentene. There you go. 2-chloro, 1-fluoro, 1-iodo-pentene. Do I have to say one ene? No. You can't have 2 pentene. Pent-2-ene makes no sense. Doesn't exist. Now, can there be geometrical isomers with this? Certainly. Of course there can be. And again, the emphasis is on the C and C bond. Let's see how this is known as easy isomerism. So here's C and C, and here's the bond. Okay? And here's one configuration where this carbon right here will have, let's say, I sticking up and F sticking down. And for this carbon, let's say you have CH3 sticking up and Cl sticking down. Okay, here's one configuration. Remember again that these bonds are fully rotating, but because these guys are not, that's why we have this geometrical isomer. That's why we're in this mess. Okay, now, the easy isomerism, this is how it works, okay? E stands for same. You're like thinking, why isn't it S? And Z stands for opposite. Okay? What do you mean by same? What do you mean by opposite? Well, molar mass is the key. Okay? So if you look at this carbon right here, and you look at what's bonded to it, other than the double bond, you have this carbon bonded to this carbon. And this carbon is bonded to this chlorine. Which one, atomic mass-wise, is more prioritized? Which one is bigger, basically? Which one is heavier? Chlorine or carbon? Of course, chlorine. Circle that. Now let's take a look at this carbon. I'm bonded to an iodine and a fluorine. Which one is more heavier? Well, of course it's iodine. Look how far it is down that periodic table in group 17. You see how for this carbon, the direction of the heavier group, say, sticks down. For this carbon, the heavier group sticks up. That is opposite. One stick down, one stick up. So to name this, we say that this is called Z. I think I messed it up. Sorry. I'm so sorry. I knew it was weird. This is opposite. This is same. Okay, so this one is actually E. I'm so sorry. E. 2-chloro, 1-fluoro. Why did I make this long name? Pentene. Okay? So what does the Z counterpart look like? Well, the Z counterpart will look like this, I guess. Okay, if we were to keep one direction the same, we'll just flip the other. As you can see, in terms of heavier group, this is heavier. For this one, this is heavier. You can see that both are sticking at the down direction. So this is your Z. 2-chloro, 1-fluoro, 1-iodo-pentene. Okay? That's pretty crazy if you ask me. So let's do a more difficult example. Let me clear this up. Now let's do a more difficult example. Okay? Let's do this one. Let's have a whole bunch of things bonded to this. Okay? I'm not even going to attempt to name this, but I can. It's actually pretty simple. Yeah, why not? Let's name this. For practice sake. So this is 1, 2, 3, 4, 5. You won't go this way because this will only go up to 4. Going this way, go up to 5. So this one wins. Yay. So hey, let's put in those side groups. So this is nothing more than 1 bromo, okay, 1 ethyl, sorry, 2 ethyl, 1 fluoro, pent, 1 ene. That's what this is. Okay, or 1 pentene, your choice, doesn't matter. But the question is this: is this going to be a E or is this going to be a Z? Well, let's check. Let's check. Take a look at this carbon right here. It seems like the more heavier group is sticking upwards, huh? Circle it. Now, this one is tough. Take a look at this carbon. This carbon is bonded to this carbon. This carbon. They're both carbon. What that means is that there's a tie. For now, round 2. This carbon is bonded to this carbon. Carbon. This carbon is bonded to this carbon again. Again, round 2 is a tie. Round 3, this carbon is bonded to, carbon. This carbon is bonded to hydrogens. No more carbon. So hydrogen versus carbon. Carbon wins. Looks like it's an E, huh? Looks like it's an E. Okay. So when you have a tiebreaker, in this case, you will go on to the next. Okay? And next. Until, of course, you see a difference. So, what if this is the case? What if there's that? What if it's not a pentene, but a but-1-ene, where the whole thing is going to be tied? Then in this case, there was no winner. There's now going to be a geometrical isomers, because geometrically is the same thing. Right? It's obvious here. There's no geometrical isomer. So you wouldn't even have E. It would just be that with a but. Hopefully you guys are happy with this. And as I said, this is not the end in terms of geometrical isomers. I will come back, okay, at the very, very end of this course section, this unit, sorry, at the very end of organic chemistry, we will be talking about stereoisomerism, and we will look at this one more time. All right, let's call it for the day. Bye, guys.